Hey everyone, this is part 2 of theoretical basics for electromagnetic sounding methods. So what's the motivation? The motivation is that we want to use electric and magnetic fields to probe the interior of the Earth. So we want to be measuring some quantities, like components of the magnetic field at the surface of the Earth, and components of the electrical field at the surface of the Earth as a function of time. We want to use this information to somehow infer this spatial distribution, variations of resistivity inside the Earth. So in order to reach this goal, it's important to wonder what is the relation between electrical and magnetic field. So let's start with electrostatics. One of the most basic law we need is Ohm's law. So we used it last week already, and you well know this relationship. You have U equal Ri, so U is in volts, R is the resistance in ohms, the intensity of the current, I, in ampere. So basically, you remember the sketch from last week. You have the current that flows into a circuit. It meets a resistor that will decrease the capacity of current flow inside the circuit. Now we need a generalization, a 3D generalization of this law, and there's a vector form generalization of Ohm's law, and it's written as such: the electrical field, which is a vector whose components are in volt per meter, is equal to the resistivity in ohm times meters times the current density vector, whose components are in ampere per square meter. So that's going to be one of the fundamental laws. Then, if the magnetic field is static, the electrical field will be independent from it, and it can be defined as E is equal minus gradient of V, where V is the electrical potential. It's basically, so of course, E has components in volt per meter, and potential as unit volts. As you could see already on last week's picture, you have the electrical field, directions of current flow, and the potential is orthogonal to it. So there's an orthogonal relationship because one is the gradient of the other. Now, let's discuss the magnetic field. So B is now unit Tesla. It's defined as the curl of A, where A is also a vector in Tesla times meter, and it's the magnetic vector potential. So we have a relation between a field and its potential field, A. So here it's important not to confuse. A in bold font is the vector, that is the magnetic vector potential, and the unit ampere, which is A, or A here. So when the magnetic field is dynamic and no more static, the electrical and the magnetic fields are dependent on each other. So you cannot define them independently. And that's now how this is formulated. You see the law for the electrical field it's equal to minus the gradient of the potential, and there is no contribution that comes from the time variation of the magnetic potential field. So that's the time variation, d dt, of the vector A. So there is a relation now. The electrical field will feel the time variation of the magnetic potential field. So let's do one more step. We take now the curl of the above relationship, so we will apply the curl operator to E, and we apply the curl to all this part here. What you distribute the curl here, you take the curl of the gradient of V minus the curl of dA dt. Now you should remember that the curl of the gradient is a zero vector. So this part will disappear, and you end up with a relationship which simplifies here to curl of E is minus the time variation of the curl of A, which, if we use the definition here, is nothing else than dB dt. Curl of A is equal to B. So you can replace this curl of A by B here. So the curl of the electrical field, now in volt per meter square, is the time variation of the magnetic field in Tesla per second. So now we have a relationship directly between electric field and magnetic field. So that's Faraday's law. Curl of E equal minus dB dt. So the curl of the electric field is proportional to the magnetic field. What does it mean? It means that if the magnetic field is not changing, so now think you're holding a magnet here, and you're not moving it. Here there's an electrical loop, and here there's a measurement device. The magnetic field is static, so it exists, but it doesn't change inside the loop because you're not moving the hand. Nothing is happening. Now, if you move the magnet towards the loop, you will induce a current, basically, just during the motion. So the time variation of B inside the loop will induce a current. If you do it the opposite direction, there will also be induction of a current, which will have a different direction. So that's an induction of current by variation of a magnetic field. So that's a very important law. The last law to be discussed is Ampere's law. So the law of Ampere, it will set up a proportionality between the magnetic field circulation and the electrical current density. And that's how it's stated. So the curl of B is equal to mu 0 times J. So this is the magnetic field, and that's the current density. Mu 0 is the magnetic permeability of vacuum. It's in Newton per ampere square. So now we have a relationship between the magnetic field and the current density. So that basically means that when a current is being conducted in a wire, it induces a magnetic field around this direction of current transfer. So there is induction of a magnetic field by current injection. So that's a summary now of the equations we will need to further discuss electromagnetic soundings. There is Ohm's law in vector form, E is equal rho J. There is Ampere's law, curl of B equal mu 0 J, and there's Faraday's law. Curl of E is equal minus dB dt. So the natural magnetic field and its variation, they will be measured in 3D, and the electrical field will be measured along the Earth surface in 2D. And the aim next will be to decipher the distribution of resistivity deep down. So we will use measurements of E and B, and we will use the combination of these different laws to try to determine the parameter of interest, which is here the resistivity. Thanks for your attention.